Hi guys. So in this first one, what we're gonna do, so we did the intro. So I'm just gonna go over to first how to clean up the geometry. So just a step-by-step walkthrough. In this, we merged. It can be the packed Verneuil cells. They don't have to be simmed, but we're gonna lock the time frame, lock them in place, unpack them. We want to compute class. I know we have the name, but this comes in handy on the points. And so we're going to put class and name from the primitives onto the points. That class is a primitive attribute. So we have an attribute for pretty much every piece. The name we have to carry through all the way. Now, what happens later in the system is I want to know that I don't want to divide these edges. So I have a bunch of groups on here that they come in. You're going to see extrude back, extrude front, extrude side, inside, and outside. Those are very important groups. Now, what I do is this side group, which is right here, this one, I'm going to promote it to points. So there is so in between, like this segment right here, that I have these points are registered as side, being on the side. That's very important because we're going to know not to divide that segment. All right, so now we can keep the front. So we're going to destroy the groups that we don't need. And you're going to see we only have the front, and the reason why I'm doing it like this is because these are flat planes, and we're pretty much going to re-extrude it downwards. Then we move the N attribute from the vertex to the point, and then we're going to separate them so we can do fuses. Or actually, I don't think I need them anymore, but oh wait, I do. Yes, we want to separate these because with this geometry, the points we want to keep that one, that one, that one, that one, and that one. And if you notice in this, these points that we want to keep, they only have 2 vertices. Really, so that's what we do here. So we make an ID attribute to transfer attributes. Convert the, I don't think I need this anymore, but I did it anyway. Actually, I think I do to connect them. But I do this thing called vert count, and what this does is I basically unique all the points, and then I connect them, and you're going to see basically all these points here, they get connected into a primitive, each one of these. Then I promote it to a primitive attribute, that ID, so the original point can look at its respective primitive and get the total vertex count of that primitive. Now that's important because then I can remove all the vert counts that are greater than 1, and this is what it gives me. And then so I can delete that attribute. So now I have the points of just the Verneuil cell. Now the next thing I have to do, and so we can just visualize this, and I showed in the group prior to that, if I build these polygons, we really get a mess here. They're out of order. The winding order isn't correct. It's totally mangled. So we have to redo that. Now the way I do that is I'm going to bring in the original geometry here. I'm going to do the packed primitives from this geometry. So I have these center points. If I go to the so this is a quick way to sample the surface. So I'm going to sample the surface. I'm going to get the normal, and I'm going to get the tangent. And the tangent's computed here on the surface. So you can see these yellow tangents here. And there's an optimization I have to make. I sample these twice, but we don't have to worry about that right now. And from that I can make a matrix. I have the tan, I have the position, and I have the normal. With that, I'm going to copy that information back onto the points. I'm going to make an ID attribute so the points can talk back to each other. And then what you're going to see here is I move them back into their position off that class attribute. So you can see this thing just they're separated into a class domain space pretty much. You know, just move them up, separate them so any fuses and near points don't collide. And then so we move them back. And then we transform it, and as you can see what happens in this transform, they all snap to the surface. Now what we get here is, as you can see, it's just invert the transform, multiply the position. We get it in local space pretty much. Local space to the object's center point. And so we build that. And then what we do is we compute cylindrical coordinate systems. What that does is that gives us a value that it basically a value that increases in this direction here, in a clockwise direction. And so I name that phi, and so here's the formula for that, and you can look it up on Wikipedia. And you can notice that I'm doing x and z going into my x and y there. That's you gotta, because these have to be the plane values. That's very important, or it won't work. And then I can sort based on that attribute. I can delete the geometry, and then I can build that polygon, and I'm going to copy this. And so basically this is just to connect, and I do it by the extrude group. So I turn the group by attribute. And there you go. I could also probably connect by name or by class on a point level. But the geometry is built now. And then I clean up some unnecessary attributes that I don't need to carry forward. Now, if your glass is curved, what you have to do is pretty much the same thing that we did here above. Is we got to add on these points. We need to average these normals out. Now, I don't have to do it on this, but if your glass has a bend in it, these things are going to diverge. And then when you extrude your polygons down, you're going to have a collision. And so all what we do is destroy the geometry, do a near point, same thing as before, make a primitive, sample that primitive, or promote the normal to the primitive, and then on the average, and that lines them all up. So you don't see a difference here, but on curved geometry you do need it. Alright, so that's pretty much the geometry prep, and the next thing we're going to go into is going to be reconstructing the geometry and the constraint network. You sort of need both of them together or they won't work. Alright, thank you for watching.